Yeah. If you can unshare, please, and
Sure.
we'll move to the next talk. And the next talk is going to be given by Jack Borosinski from University of Hawaii. Jack, can you hear us?
Yes, I can hear you.
Wonderful. The title of the talk is NULAT, Compact Anti-Neutrino Detector. So please share your screen when.
Can you see it?
Yes.
Great. Now I will set it to presentation. Well, hello everyone. My name is Jack Boroshinsky, and I'm a second-year graduate student under John Learned. I'll be talking today about NULAT, our new compact anti-neutrino detector. NULAT is a compact segmented neutrino detector with aims to demonstrate reactor monitoring for the purpose of identifying diverted plutonium. As neutrino signatures can't be hidden or falsified, their signal can be continuously monitored, and the monitoring can be done in a way that does not impede energy production. This is a prime method for reactor monitoring. Additionally, we hope to use this detector to probe reactor anomalies where previous experiments have found results inconsistent with the standard model of neutrino oscillation. One potential theory is the existence of additional sterile neutrinos beyond the currently recognized 3. Testing this will require a spatially accurate detector that can work in high background area near a reactor core to study the short baseline neutrino oscillations and compare to the results to theory. Additionally, we hope to contribute to the study of uncertain absolute neutrino flux from reactors. We are also in the early stages of discussion on our detector's capability to get neutron directionality. This would be useful for the detection of special nuclear material through the neutron spectrum and could give better neutrino results by allowing us to disregard events coming from directions other than our known source or distinguishing between multiple sources. The NNSA mission, as stated, is to work globally to prevent state and non-state actors from developing nuclear weapons or acquiring weapons-usable nuclear or radiological materials, equipment, technology, and expertise. We hope to contribute in the prevention of acquiring weapons-usable nuclear materials through active monitoring of nuclear reactors and the accurate detection of replaced rods in the core. As I had said earlier, the neutrino signal cannot be hidden or falsified like other detection signatures such as heat monitoring can. So our detection of any changes to the core will be fast and have guaranteed accuracy. This has been said several times before, but as a background for neutrino detection, we'll be employing the interaction known as inverse beta decay, shown in this diagram, where an incoming neutrino, over here shown in black, interacts with a proton in our detector, producing a neutron, shown in blue, shown in blue, carrying most of the neutrino's momentum, and a positron, shown in green, carrying most of the energy. The fast positron quickly scintillates on the scale of nanoseconds, giving a start signal and information on the neutrino's energy. The slower neutron goes through several collisions, over here, traveling randomly through the detector until it's captured on lithium-6, giving it an approximately 7 microsecond delay that we use as our stop signal. Neutron and positron events can also be separated through pulse shape discrimination, where the decay tail of our pulse will appear different for each particle. Using what has been named a Raghaven optical lattice of scintillating cubes, we are able to effectively channel the majority of light along an interactions axis, giving us good spatial resolution of where each event happened. Our demonstration Raghaven optical lattice consists of a 5 by 5 by 5 array of 2.5 inch scintillating cubes with a 0.01 inch air gap between them and a light guide PMT setup on each cube face outside the lattice. Due to the difference in the index of refraction between our cubes and the air between, we utilize total internal reflection to channel light and recover the location of an event. You can see in the top graphic our lattice channeling colored light for a visual demonstration, and in the lower graphic a simulated output of one lattice face when an event takes place in the center of our lattice. You can see that the large majority of light is channeled along the event axis with some light leaking further away. Combining good spatial resolution, time, and energy data with our understanding of the inverse beta decay process, we can separate our neutrino signals from background events, allowing us to get good results with a small detector and in high background locations. Our background rejection comes from a combination of the known time delay between the positron and neutrino signals, or positron and neutron signals, which is approximately 7 microseconds, pulse shape discrimination, distinguishing which particle produced each event, geometrical correlation, as simulations have shown that 25% of our neutron-positron events occur within the same cube, and 60% of events occur within one cube and its closest neighbor, allowing us to disregard spatially distant events. And expected energy values, as our interaction gives approximately 400 keV neutron signal and a positron signal correlating to the original neutrino energy. So only when we see a positron signal followed by a 7 microsecond delayed neutron signal in a small section of detector are we truly seeing a neutrino event, and everything else can be ignored as background. The image on the right shows a simulated reconstruction, with red highlighting the collected photons in a PMT and blue giving the expected location of the events that caused it. Down there. Present tests with our LEDs, laser light sources, and simulation have been positive, showing the effectiveness in the Raghaven optical lattice's channeling capabilities. Our use of 0.5% lithium-doped cubes was found to be ineffective, as the cubes quickly developed a powdery film and lost transparency. Currently, they are replaced with a standard LGen simulator, though we plan on moving back to a lithium-based simulator soon. Finally, we've been able to effectively measure muons traveling through the detector. The top image shows the efficiency of light traveling down a test 15 by 1 by 1 cube system with PMTs on each end, demonstrating the Raghaven optical lattice's effectiveness in channeling the light. The lower image is of a lithiated cube that has gone bad. The cube, as you can see, has become tinted slightly yellow brownish, and there's a thin crystalline film visible on the lower left corner, making it not optically sound for transporting light anymore. If successful, this detector will be able to remotely and unobtrusively monitor reactors for the diversion of illicit materials, aiding to the NNSA's mission. We also plan to take precise measurements of the electron-neutrino spectrum to track down sources of previous anomalous measurements and verify the existence or non-existence of additional sterile neutrinos beyond the standard model. Mainly, we have collaborated with Lawrence Livermore National Lab, who are making their own geometric neutrino detector. Collaborators from there include Slava Lee and Stephen Daisley. Slava has been on several of our weekly meetings and contributed to discussions such as producing better lithiated cubes that don't go bad, and the potential for other materials in our air gap. We are also collaborating with Charlie Rasco from Oak Ridge National Lab, who has been involved in this group on previous projects and contributed to our simulations. In conclusion, recent progress has been promising for the success
I think we have lost the speaker.
Hello, did I lose the meeting?
Just for a moment.
You're back. We can hear you, but if you can please reshare your screen.
I did not notice it get lost earlier.
At least I don't see it. So if you could please unshare and share again.
Do you know how far back I lost connection?
Just about 10 seconds, not long. So
I can't hear you very well. It's breaking up.
Only about 10 seconds of audio we lost. At least from my side, I lost about 10 seconds between the time that I lost you and when I heard from you again. So.
Yeah, Jack, can you hear me?
Yes, I can hear you.
Yeah, we just lost you right at the end, so you didn't really miss anything. So if you can just pick up right where you were on the MTV Impact slide, that would be great.
Okay, yeah, I think one slide further in the end, but yeah, I'll go back there.
Yeah.
Slideshow, MTV Impact. Yes. So mainly we've collaborated with Lawrence Livermore National Lab, who's making their own.
Sorry, can you reshare? The screen share is not working.
Oh,
yeah.
Sorry.
No worries.
Not realized that got lost too. Back?
Beautiful, thank you. Go ahead.
Great. So we have collaborated with Lawrence Livermore National Lab, who are making their own geometric neutrino detector. Collaborators from there include Slava Lee and Stephen Daisley. Slav has been to several of our weekly meetings and contributed to discussions such as producing better lithiated cubes and the potential for other materials in our air gap. And we've also been collaborating with Charlie Rasco from Oak Ridge National Lab, who has been involved in this group on previous projects and contributed to our simulations. In conclusion, recent progress has been promising for the success of this detector. Aligning with the goals of the NNSA, we will be able to contribute to preventing diversion of weapons-usable nuclear materials. An improved understanding of the reactor electron-neutrino spectrum will be beneficial for future reactor monitoring and general physics. And when completed, we will be able to unobtrusively and effectively monitor reactors. Next steps in our experiment is to run radon through our detector to verify and calibrate its ability to work with a multi-particle time-delayed trigger and our ability to do pulse shape analysis on our signals. Additionally, we are working to complete a GANT4 simulation for our detector, and further future plans involve characterizing our response at a real nuclear reactor, trying a liquid scintillator version of the Raghaven optical lattice, and scaling from a 5 by 5 by 5 cube detector to a 15 by 15 by 15 cube detector. I would like to thank the NNSA and DOE for continued support of these research activities. Are there any questions?
Thank you, Jack, for the very nice presentation. And this talk is open for questions. So please either send the question through the group chat or raise your hand.
I have a question, Igor. I can't raise my hand because I'm a host. It doesn't work for hosts.
Sure. Go ahead.
Jack, you mentioned a collaboration with Livermore and potential alternate materials for the air gap. Can you speak a bit more about that and what those materials might be?
So it had been some early discussion still, but we were thinking about using something like aerogel for our air gap, as it would help add some structural support and still have good air-like index of refraction. Was the main idea that we had been going around and discussing with him and his collaborators over there.
Great, thanks.
Okay, I'll ask a question which is related to your geometry. So this idea of segmentation has really gathered a lot of traction in the community for the purpose of reducing the backgrounds and achieving directionality. So can you comment on the choice of the geometry and potential advantages that you get from the 3D segmentation as opposed to 2D segmentation? Because in both cases, you can reach three-dimensional position sensitivity, but what does the three-dimensional segmentation of detector medium bring you?
I am not fully sure what would be the major advantages besides that it's uniform in all directions and we can go and get no differences in our spatial resolution from getting neutrinos from different sources, and that it seems to work pretty effectively for channeling all the light, and I don't really know comparatively how well the other ones are working.
Great question also from Professor Wichi, which is I think a similar question, which is talk about the Ragavan optical lattice and sort of the origin of that concept. Where does it come from? Can you give us some background?
I believe it was an idea of Bruce Vogelaar from Virginia Tech when they were doing an earlier solar neutrino experiment that they later teamed with us and are collaborating, bringing that from their side, and we're bringing electronics from our side in Hawaii.
Thank you. Yeah. And are there any other questions from the group? I have a question which is related to your material use. So you measured you discussed there was this powdery film that developed in your scintillator. So do you have any idea what happened there? Was it environmental? Is there something else that, something you could do to prevent that from happening? Because environmental factors have been known to affect plastic scintillators. So is that something resolved just by environmental control, or is there, is it more fundamental to the material that was used?
We think it may just be the high lithium in the cube is reacting with air or something else around. And we had talked about potentially having nitrogen run through it to go and protect the cubes. But by the time we had found out about it, it was already too late for these ones. And so we're hoping to find a manufacturing method or use a liquid simulator that produces cubes that don't tint.
So if you use liquid simulator, you have to use some encapsulation, and as a result, you would lose some of the energy of the positron. Would that be an issue in these measurements or no?
I believe for the liquid simulator, the idea is to use acrylic dividers with air in between them as our separating medium. And as far as I know, we haven't done any like tests on it yet. We're still building our structure to put those lattice pieces into, but it's just an alternative right now once we found out these cubes have gone bad.
Okay. Any other questions for Jack? I think one other question which was on my mind also was also related to something you alluded to at the beginning, I think, which is that you could use this detector for other types of measurements that are relevant to non-proliferation. So I assume that you are thinking about neutron detection. Is that accurate, or what other measurements?
Yes, neutron detection is something we had thought about, but it has only been in like very early stages of discussing, yeah, we could probably do this, and we might have to think about adjusting our geometry to optimize for that. And we're also, like I was saying, looking for reactor anomalies at very short baseline experiments, or we hope to.
Okay, well, let's thank Jack on this really interesting talk. We look forward to seeing a lot of interesting results as we move forward. Really exciting concept. Thank you, Jack.